So I think we should get started, and so today we're going to talk about how we apply the wonderful things that we learned last time, that is how to formulate the derivative of a field in such a way that you obtain something that is covariant. And that is an essential tool in understanding how to write down equations which are manifestly covariant, because equations in special relativity already involve derivatives, so we have to know how to do that. Right, so we're going to talk about general effects of gravitation and how we can write some of the basic equations that describe the interaction between, say, matter and a gravitational field based on a form that is manifestly covariant. So one of the ingredients, as I said, is the fact that we learned that the right way to take derivatives is through this covariant derivative, right? And so this is the ordinary derivative of a vector with respect to the coordinate. And then we got to add another piece, right? And that piece involves the affine connection, right? And so if we do that, then this is the covariant derivative. This is a genuine tensor. This object is a genuine tensor, so it transforms in the way that we expect, which means that when we use it to construct equations, they will be manifestly covariant. So now what we do is we go back and look at the repertoire of equations that we wrote down in the case of special relativity and see how and which way we can promote those equations to a form that is acceptable as far as general relativity is concerned. So the procedure is going to be first of all, replace the metric eta alpha beta that we had in special relativity. We're going to replace that by g mu nu. And of course, that g mu nu will now depend on x, whereas in the case of special relativity was a constant. And so the second ingredient is the one that we learned last time, and that is that we replace the derivatives by covariant. By covariant derivatives, and that should give us equations which are acceptable. So let us look at some of the simplest equations in special relativity. So if you have a point particle, for example, you have du alpha by d tau is equal to 0, right? And so that would be the equation for a particle that is not subject to any external force. And the equation for the spin would be that ds alpha by d tau is equal to 0. So this would be for the forward velocity, and this would be for the spin, right, if the particle has a spin. And so these are the special relativity equations. And so it's easy to see how we promote those. But the first thing, of course, we have to use is, because we have derivatives, that we need to use the correct definition. Now, in this case, we also have a constraint, which is u alpha s alpha is equal to 0, right? We also had that, by the way. You can always enforce the orthogonality of the spin vector to the forward velocity vector. And so we're going to promote those equations to something that looks acceptable, which is, first of all, du mu by d tau. So use of the covariant derivative, in this case, along the path of the particle. And so this is going to be equal, when we write it out in components, this is the ordinary derivative with respect to tau. So du mu by d tau plus gamma mu lambda sigma, and then u mu u sigma. And this is going to be equal to 0. Right? So that's equation number 1. And equation number 2, well, of course, this is just the equation for free fall. Right, so it means that we really haven't learned much at this stage, right? Because just using covariant derivatives reproduces what we had known before. But for the spin, we get something that we haven't seen before, and that is that the derivative of S mu with respect to d tau is equal to the ordinary derivative of S mu with respect to tau, right? ds mu by d tau. And then because this vector here is we're going to write it in the covariant form, is equal to minus gamma lambda mu sigma, and then times nu nu gamma lambda mu nu, and then u nu u lambda s lambda in this form. And so this is also going to be equal to 0. And so that replaces equation 1 here and equation there. And of course, we have also again the constraint that u mu s mu is equal to 0, right? We can enforce that as well, right? And so that's going to be the new set of equations which applies in arbitrary gravitational fields, right? So this applies to arbitrary gravitational fields, right? And so the gravitational field is in here, is in the gamma, right? The gravitational field comes in at this point because the gamma contains derivatives of the metric, which is in turn related to the gravitational field. So the second equation is of some interest, in which case, well, when we're talking about something that spins, and so usually think of the spin of a particle, but nevertheless you can also have a macroscopic object that has a spin. So the second equation is of relevance when you look at the Earth and you put a satellite in orbit, and that satellite in orbit has a spinning object, right? So there's something that spins like this, for example, some sort of gyroscope. So if you have a gyroscope in orbit, then it will be, when it is in orbit, of course, it is free falling, right? It is under the influence of a gravitational field exclusively, right? There might be other fields, but they're usually quite weak. And so because of that, a gyroscope that is orbiting the Earth is in fact described by this second equation. Right? So any sort of effect that has to do with the precession of the axis of the gyroscope, and there's some complicated motion that arises in general relativity because of that equation, any sort of effect is described by that equation and can actually be tested. There are in fact experiments. There is a notable one that went up a few years ago where actually they tried to test the predictions of general relativity for orbiting gyroscopes. So they had a large niobium ball that was suspended, and they were able to look at various effects to see if it was in agreement with GR. So it's a very interesting problem, and it's described by this second equation. Now, if you have forces that are non-gravitational, then those would be described by, in special relativity, by this force, F alpha, right? And so you remember that in special relativity, so we had this equation that involved the F alpha, which just says that the derivative of the force velocity is equal to F alpha. So we can promote that here as well. And so that means that in our case, we are going to have, instead of the ordinary derivative of the force velocity, we're going to have this covariant derivative. And now we're going to get on the right-hand side a term which is coming from this force. So that is going to be not an F alpha, but it will be an F mu, and it will be divided by m. And this, again, is a generally covariant equation. And And so this force could be, for example, due to electromagnetism, right? Or it could be lots of other things, right? Well, if it is due to electromagnetism, then, of course, it is just the Lorentz force. Right? It's just the Lorentz force. So in the case of the Lorentz force, we can write that out explicitly, right? Because in the case of the Lorentz force, if you remember, we gave the expression for it in special relativity. And so now we just need to promote all those indices to quantities that are acceptable in a general relativistic context. So the force would be E times F mu nu, right? So we have the electromagnetic field strength tensor, which contains the E and B field, right? And then we have the velocity, because that is what, of course, appears in the Lorentz force equation. So dx nu by d tau. And so that would go in there. Right? That would go in there. And so we have that left-hand side is acceptable from a general relativistic context because it involves a 4-vector, and you take the covariant derivative of that, which contains two terms, the ordinary derivative and the affine connection. So this is a good quantity to have. And what appears on the right-hand side is also a genuine 4-vector, because it is constructed out of the energy moment, out of the field strength tensor with indices, which are general relativistic indices and involving, again, the 4 velocity. So as it stands, this is a good equation. And in fact, we can write this out. In the following form. We can write this as bringing the mass over on the other side. We can write this as the second derivative of x mu with respect to tau squared, right? Equivalent form, right? So that's just the derivative of the 4 velocity, ordinary derivative with respect to tau. But of course, the 4 velocity itself, right, u mu, is just dx mu by d tau. So we write that out explicitly, and we leave that on the left-hand side, and we bring over on the right-hand side, next to the first term, the contribution from the affine connection. So we can write this as the F mu we have over there, and then minus m times the gamma mu, right? And then lambda sigma dx lambda dx sigma divided by d tau, right, in this way. So that means that the equation of motion for a particle involves, right, this is just ma if you want, in the 4-dimensional space-time version of that, involves some electromagnetic force, right, or in general a non-gravitational force, right, of some sort. And then the remaining term is the gravitational force. Right? So the gamma term is the forces that are due to gravity. And if you want, you can write them out explicitly, or you can just leave it as it is. Right? So this was just for the particle dynamics. Right? And so the next step is, if you have a spin, you can do the same argument. Right? So repeat. Argument for spin. Right? So we have something that is like this. Right? And again, we write out the equation, first of all, in special relativity. Right? I think we wrote those down some time ago. And the equation for a spin is that ds alpha by d tau, right, was equal to u alpha times f beta divided by the mass, times S beta. So this is again the 4 force, right? And if there is an external 4 force, which could depend on x, then the derivative of the spin with respect to proper time obeys this equation, right? And so we want to promote this to general relativity, right? And to promote this to general relativity, we have to change things a little bit, because this has to become a covariant derivative. And on this side, we have to have, of course, the for velocity u mu, the f mu, and the spin, right? So we write that ds mu by d tau, right? Covariant derivative, which contains 2 terms, is equal to, and well, on this side, we don't need to do a whole lot, because we can just write this as u mu and then f nu divided by m, and then times s nu. And that's it, basically, right? So now we can take the term that appears here, which has the affine connection in it, which is the angle of this term, and we can move it over on this side. And, well, we will not do that, but you can separate the gravitational force contribution. Gravitational force is in here, right? Gravitational force is in one of the 2 terms in here. And this part here is the non-gravitational 4 force, so the one that arises because of electromagnetism. So this is called the Fermi-Walker transport. The second equation is called the equation for the Fermi-Walker transport. So it tells us how a spin will behave if you are in a gravitational field, and there is some other field as well, like an electromagnetic one, that acts on this body as well. And so, of course, the Fermi-Walker transport, when the external force is 0, then it falls back into the ordinary parallel transport. So that means that this side is 0, and the only force that is acting on the spinning object is the gravitational force. So now let's look at electromagnetism, right? So next exercise. Promote electromagnetism to a general covariant invariant form. So that means, again, we go back and look at the equations for electromagnetism in special relativity. Well, those are just Maxwell's equation, right, rewritten in a way that involves this f alpha beta. So the derivative with respect to x alpha of f alpha beta, right, is equal to minus j beta. That is how we wrote it last time. And so these are the unhomogeneous equations for the electromagnetic field, and plus the homogeneous one. So d by dx alpha of f beta gamma plus d by dx gamma f alpha beta plus d by dx beta f gamma alpha is equal to 0. Right, so it's set number 1 and set number 2. And so promote these to a general relativistic form. And well, that again is easy to do, because it means that every derivative that appears in here is going to be written as a covariant derivative. And now we do have a very simple and nice notation for covariant derivatives, and that is the semicolon thing, right? So first of all, the f will contain indices mu nu, right? And then we have this derivative here, and that has to be a covariant derivative, right? And so that's going to be semicolon lambda is equal to minus j. And then we sum over, right? Nu is equal to minus j mu, right? So that's the first equation. And the second equation is, well, that one. So f mu nu semicolon lambda plus f lambda mu semicolon nu, right? Plus f nu lambda semicolon mu is equal to 0. Now, those look rather complicated, and in fact, it's possible to simplify. It's possible to simplify, and the reason why you can simplify these is because in this case you have a covariant divergence. You see, you have a derivative, but then these indices are summed over, right? And we saw last time that if you have a covariant divergence, then the result is actually simpler. And the second one involves basically a curl. So you do a little bit of algebra and you simplify that. And for example, in the curl, all the gamma terms cancel out, which is kind of remarkable. And so we get, for the first equation, we get d by dx mu. So the covariant divergence can be rewritten just in terms of the metric in this form, d mu f mu nu is equal to minus j nu. So that's the first equation. And the second equation, as I said, all the gammas drop out, and we have d by dx lambda f mu nu, right, plus cyclic permutation, so d by dx nu f mu lambda, or f lambda mu, plus d by dx lambda, d by dx nu of f nu lambda is equal to 0. So no gamma lambda mu nu here, right? So all the gammas drop out, and you just have the ordinary derivatives. And in the first case, you notice that if it wasn't for this root g, then this would be exactly the same form as in special relativity. So the only changes is this square root of g, right? Now, in fact, there is an equation number 3, which is current conservation. And so that is that the derivative of dx mu of the square root of g of j mu is equal to 0. So in fact, so plus continuity equation. Right, plus the continuity equation, which is again a divergence equation. So again, even in the current conservation, there is only this very minimal change. So that's kind of remarkable. So the change is very minimal. Change is very minimal. I mean, you might have expected that all sorts of strange combinations of the affine connection would come in when you were coupling electromagnetism to gravity. And that is not the case. The only thing that appears is the metric. Well, it's even simpler than that. It's just a determinant of the metric that comes in, right? It's just the square root of g, right? You remember that g is minus the determinant of g mu nu. So that's the only thing that appears in there. And so that doesn't mean, of course, that the coupling is weak, right? Because the gravitational effects are there. So the photon equations, right? Maxwell's equation, which describes the propagation of a photon, still contains gravity, you know, in a number of places, but it only contains these two determinant of the metric. So we might have expected that things would be more complicated, but they aren't, right? Nevertheless, the photon couples to gravitation, right? It is affected by by the presence of those G terms, right? So the G term reflect the presence of a gravitational interaction for the photon, right? So now, that's all there is to say about electromagnetism. It's nice that we can, dispose of this aspect very quickly and without having to plunge into lengthy calculations. So another aspect that I would like to look into is the following, namely what happens to the energy momentum tensor. What happens to the energy momentum tensor, because we spent quite a bit of time in special relativity talking about this T alpha beta, which was conserved, right? Conserved quantity. And so we had, in particular, we had dt alpha beta with respect to x beta. The derivative with respect to some coordinate was equal to 0 if there were no external forces. So these represent external forces. Right? So if the external forces are 0, then the energy momentum tensor is conserved in special relativity. And so how do we promote this to GR? Well, again, we replace derivatives by covariant derivatives. So we just have T mu nu, semicolon nu, is equal to G mu, right? Where now the external forces are represented by this G. And, well, this can be expanded out, because we do know that when you take a covariant derivative, you get affine connection terms. We also know that when you get a divergence, things simplify a little bit. Right? So let me write out the expanded form for that. Right? The expanded form for that is that 1 over the square root of g. Again, every time you have a divergence, you can rewrite that in terms of some appropriate ordinary derivatives and the determinant of the metric, or the square root of the determinant of the metric. And so in this case, you get the derivative with respect to x mu of the square root of g of T mu nu, right? And well, that's not the only piece, right? There's a second piece we can write out in a moment. But the first thing I'm going to write on the right-hand side is this G nu, right? And then, so the covariant derivative always contains some gammas, and those gammas are going to be in here as well. And so there is a second term, which is gamma nu, lambda sigma, right? And then times T lambda sigma, right? So now we can stare at this expression a little bit more, right? And so that expression tells us that first of all, the covariant divergence of the energy momentum tensor is 0 if there are no external forces. If external forces are present, then there is a contribution in here. And if you look at the ordinary divergence contains this term and also contains a purely gravitational contribution. So in other words, even in the absence of external forces, the ordinary divergence is not 0, right? So whatever flow of energy momentum you have due to the matter contribution, there's going to be a piece of it that involves explicitly the gravitational field. So the gravitational field is in here, right? The gravitational field appears in the gamma affine connection. And of course, it appears also here, right? It appears also here. So you have that the conservation of energy and momentum is not trivial, right? Because the metric appears in all sorts of different places, right? So when the energy content of matter changes, it gets transferred, part of it, to the gravitational field through these terms, right? It's the total balance that is in fact equal to 0 in the absence of external forces, which contains both the ordinary derivative term and also the affine connection term. So this conservation law, in other words, is not trivial in the sense that there are several pieces that you have to take into account, and you cannot just naively say that it's just the divergence of the T mu nu, which is 0. Even ignoring this factor, right, there is another piece that has to do with a gravitational contribution proportional to the T mu nu itself in this case. Right? So anyhow, that is, of course, something that will be very useful in a number of cases, in particular when you discuss cosmological applications of Einstein's field equations, right? There's going to be some matter. Right? The matter will be described by the T mu nu. Usually that is modeled either by a set of n particles or more appropriately by some sort of perfect fluid. Right? So the conservation laws of the energy momentum tensor for the perfect fluid will involve both of those terms, because it is the covariant divergence that is 0, but where the covariant should be underlined, because covariant divergence is not the same as the ordinary divergence. There is also this gamma term, right? So this is one of the fundamental equations, in fact, when we deal with cosmology, that we have to always keep in mind, right? And we are, of course, going to assume that the matter energy momentum tensor is conserved, and that this conservation law applies for the kind of cosmology that we will be looking at. So one last item that remains is hydrodynamics. Right? Hydrodynamics. So again, in this case, we are going to look at the perfect fluid that we discussed in the at the beginning of this class. I think it was the third lecture in special relativity. So we had this perfect fluid, right, on which something like 90% of modern cosmology is based on this perfect fluid description of the Friedmann equations. And so the energy momentum tensor for the perfect fluid is one where you just have a dependence of the energy momentum tensor on the velocity distribution in the fluid, right? And so it is a pressure term which involves the flat metric. It has this form, P times 8 alpha beta. And then there is a second term that involves the velocity, and that is proportional to the pressure and the density, and then so times u alpha and u beta. So there's a pressure, and there is a density for the fluid, right? In the simplest cosmological applications, the pressure and the density are going to be functional of the time being the time since the Big Bang, so the cosmological time. And usually there is an equation of state which relates one to the other, right? The pressure in most simple models is just proportional to rho. And we discussed in the first few lectures on special relativity that if you have a non-relativistic fluid, then W is essentially 0. You just have the density and the pressure is negligible. And if you have a relativistic fluid, then this W parameter is taken to be 1/3. Right? So if you're talking about photons or neutrinos, W is 1/3. And in fact, it will turn out that when you discuss the cosmological constant, you can force it into this form and just take W to be -1, because for a cosmological constant, you only have the first term. So this is kind of a neat thing to play with, this perfect fluid form. And it describes all sorts of different ingredients in the cosmological evolution, and which can be then worked out analytically without too much work. So how do you promote something like this to a general relativistic context? Well, you have to write things in terms of the metric G mu nu, right? And well, that is very easy to do, right? Because you write that T mu nu is equal to P times the metric G mu nu, or the inverse of the metric in this case, plus, and then P plus rho. And we've already encountered the full velocity many times, so there is no issue in writing this as mu, u mu, and u nu, right? And that's it. So we know that this is a genuine general coordinate tensor because for velocity we know is a 4-vector, and when you take products of 4 vectors, you get genuine tensors. They transform in the right way. We also know, of course, that the metric is a tensor, covariant or contravariant, depending on whether the indices are upstairs or downstairs. We also know that when you add together tensors, you still get a tensor. So everything works out fine. There's nothing that we really have to do. The promotion to a general relativistic form is kind of trivial, right? So now the only other thing that we might be interested in is what is the divergence of that thing. And so again, that's a little exercise that one can carry out and see what one gets. So divergence of above, right? So we take T mu nu and semicolon nu, right? And so now we'll look up what the expression is for the covariant derivative of a 2-index object. In this case, the T mu nu, or perhaps more appropriately for what the covariant divergence is, because we are taking a divergence because we are taking those 2 indices to be the same, right? So this is going to be some ordinary derivative plus an affine connection term. And of course, in addition, we have to do that for both terms. And in general, we cannot assume that the pressure or the density is constant everywhere, so there's going to be derivatives of the pressure and derivative of this thing. What about the derivative of the metric? Well, if you paid attention in the last class, then you would have remembered that always the covariant derivative of the metric is 0, so that term is not going to contribute, right? So we get the derivative of the pressure with respect to the only index that's left over is this mu index, so d by dx nu times g mu nu, right? And then plus 1 over square root of g times the derivative with respect to x nu times square root of g of p plus rho times u mu u nu. Right? And well, whenever we do a covariant derivative or a divergence, we're going to end up, unless there is some miraculous cancellation, we're going to end up also with an affine connection term. And that, of course, we have here as well. So we have a gamma mu nu lambda of p plus rho, and then u nu lambda. And well, that is supposed to be conserved because we don't want energy and momentum to just disappear in certain places, right? So locally, at every point in space-time, we still insist that there is a local conservation of energy and momentum. And so that means that this covariant derivative has to be 0, right? Has to be 0. And so these are the hydrodynamical equations. So there are a set of non-trivial equations that will tell us how energy and momentum flows locally. At every point in space-time, it tells us how this is going to happen, and it will go in accordance with that equation. And but the equation is fairly easy to write down, and so there it is, all right? And we will find, and I think this is something I already mentioned in the last lecture, that you do learn in electromagnetism, right, when you look at Maxwell's theory, that electromagnetism is inconsistent. Maxwell's equations are inconsistent unless the current is conserved, right? You can't have Maxwell's equation without conservation of current, right? The continuity equation is has to be satisfied by Maxwell's equation. By taking divergences of left and right-hand sides of Maxwell's equation, you find that you don't get a consistent answer unless, of course, the continuity equation is satisfied. So here the same thing is going to happen. Einstein's fields equation, the equation for gravitation, are not going to be consistent unless the energy momentum tensor satisfies exactly that equation. Right? The covariant divergence of the energy momentum tensor has to be 0 no matter what we're looking at, what type of matter, whether it's a fluid or end particles or dark matter, whatever it is, the total the divergence has to be 0, right? And so that will be something that will reappear later on. Of course, we have to keep in mind that in general, the so-called matter energy momentum tensor will contain many different contributions. So the matter energy momentum tensor will contain, well, dirt, right? Atoms, molecules, us, all sorts of things. Will contain photons, electromagnetic radiation in whatever form, magnetic field, radiation, whatever it is. It will contain things that are a little bit more elusive, like neutrinos, right? They will be in the T mu nu as well. And of course, the T mu nu's are additive, right? So the more components you have, the more things you keep on adding to this T mu nu. And it will contain other mysterious things like dark matter, for example, right? Dark matter T mu nu will be in there as well. So this conservation law, of course, in general, will apply to the sum of all those things, not individually, right, but to the sum of all of them. So, very good. Now, one last topic remains to be discussed, and that is curvature. Right? So before we proceed to the field equations, we still have to address the issue of what kind of terms you can have in the field equations for gravity, which are manifestly general coordinate invariant. And so you remember that one of the issues we had, one of the problems we had, is that in general we expect, like for electromagnetism, right? In electromagnetism, what enters in the Maxwell's equation are derivatives of the electromagnetic field, right? And you find out that there are certain combinations that will give you Maxwell's equations, which are things like d nu a mu, like this, right? And then times d mu, that is equal to the current, where you end up with an object of this type, right? So you have to take derivatives of the field, and then that gives you the equation. So the problem with the metric is that, well, we understand that that has something to do with the gravitational field, right? And so the first step is to take a derivative of this thing. And unfortunately, as soon as we take a derivative of this thing, it has the nasty, rather nasty property that the derivative done the right way, right, so that you get from a tensor another tensor, right, the derivative done the right way using the covariant derivative is identically 0. Is identically 0. It doesn't matter what the metric looks like. Any metric will satisfy this property because of the definition of the covariant derivative in terms of gamma. Right? So that's a problem, because if this is 0, of course, if you take another derivative of that thing, it's still 0. So you get nowhere. Right? So there is a little bit of an issue here. Right? And so the way out of that was solved by Riemann and Christoffel. Right? Around 1869 or so, right? And they figured out that, in fact, there is a thing that you can construct out of derivatives of the metric, but the construction is a little bit more tricky, because you actually start from the affine connection and take derivatives of that. Now, remember, the affine connection is not a tensor, but that does not prevent you from taking derivatives which are not going to be 0, and then you can find some combination which is, in fact, a genuine tensor. So Einstein had to put up with all this complexity, right? He started to look at this in 1912, right? I mean, the program of differential geometry was kind of completed in 1901, right? So it was started in the latter half of the 19th century. Around 1901, people had figured out most of the mathematical ingredients you needed to formulate the mathematics of curved space in 4 dimension, or in fact in any dimension greater than 2. In 2 is really a simple case. And so that was done by Ricci and Levi-Civita, who introduced all these wonderful identities that we partly talked about, and then we'll talk about some more. And Einstein was completely unaware of all this work until, as I mentioned previously, Marcel Grossmann mentioned to him in 1912 that there were these papers that they should look at. And you remember that I mentioned in the very first lecture that Einstein understood that somehow when you talked about accelerated observers, space-time could become curved, right? Because you have this example of a rotating disk, right? If the disk is rotating at sufficiently high speeds, then the relationship between the radius and the circumference is not what you expect on the basis of Euclidean geometry, because the circumference gets length contracted, right? Because of the relativistic effect. The perimeter gets shorter than 2 pi r, and so it looks like the space-time is curved. So he understood that maybe curvature was actually something important that should be considered. And so Grossmann pointed out to him all this wonderful paper, and they started to learn differential geometry. And all of a sudden, they found a number of results that were very much relevant to what they were discussing. In particular, Einstein understood very early on that the gravitational field was not described by a single field, phi of x, but instead should be described by something that had a lot more components, 10, right? And so that, in fact, was precisely the key ingredient in all of the mathematics that Riemann and Christoffel and Ricci and Levi-Civita had developed. The metric was the central object, right? Everything came out of this metric by taking derivatives, right? So now there's well, some lengthy discussion that one can do at this stage, and that we will not do here because of lack of time. And but the point of this, and I'll just write out the result in a little bit, is the point of it is that if you look at gamma lambda mu nu, right, at gamma lambda mu nu, the affine connection, this is not a tensor. Not a tensor, right? So, well, we learn to live with that. It appears in all sorts of equations. When you write them down explicitly, the covariant derivatives have this gamma term, right? It's not a tensor, but we have it, and we know how to deal with it. And that means that we should not be shy, and there is no reason to calculate derivatives of this thing, right? So we can calculate derivative with respect to some other index, right? So, for example, with respect to x sigma of gamma lambda mu nu, right? And, well, the derivative, of course, is not going to be a tensor either. You started out with something that is not a tensor, and you take a derivative, and God forbid you even take an ordinary derivative and not a covariant derivative. This thing has not a chance of being a tensor. But what you can do, and what Riemann and Christoffel discovered, is that there's all sorts of different combinations for these indices, right? You can have this mu interchange with the sigma. So you can take the derivative with respect to x mu of something that has a sigma in there. And so plus lots of other combinations. Lots of other combinations, right? And so the hope is that by the time you play around with all these different combinations, that there could be something that you can eventually construct that transforms like a tensor. In other words, all the parts that don't transform like a tensor cancel out. And so that was the discovery, right? And that object is the Riemann tensor. So you can construct out of all these derivatives of the gammas, you can construct something that is in fact a genuine tensor. And it is not something that you can write simply as a covariant derivative of the metric, because that is identically 0, right? So there is this thing, and so we're going to write out its form next, right? Right? Riemann tensor. Right? So it is defined in the following way. So it's called R. It is customary for a lot of the things that we're looking at shortly to write the first index upstairs and the remaining indices downstairs. But of course, you can write the indices any place you want by raising and lowering them with a metric. And so it's mu null k. Right. So it is the derivative of gamma lambda mu nu with respect to xk, right, minus the derivative of gamma lambda mu k with respect to x nu, plus gamma lambda mu nu times, gamma eta. We need to introduce one more index. Gamma eta mu nu, and then gamma lambda k eta, and then minus gamma eta mu k times gamma lambda eta and nu. Okay. So that's the definition. So you recognize that it does contain derivatives of the affine connection, which are individually, of course, not tensors, right? But the combination that you have here, if you just took ordinary derivative, that would not be a tensor either. But if you have products of the gammas, right, then you can construct something that is a genuine tensor. So this is a genuine tensor because if you look at the transformation properties, right? So if you look at the transformation properties, then R prime, right, under general coordinate transformations, R prime of tau rho sigma eta. This is supposed to be a tau, right? So this transforms as a genuine 4-index object, which is covariant in these lower indices and is contravariant in the upper one. Now remember, whenever you have the lower indices, it transforms according to dx by dx prime. When you have the upper index, it transforms according to dx prime by dx. So this is equal to, so we have a dx prime, tau by d lambda, and then 3 dx's, so times dx by dx, dx by dx, and dx by dx, where the bottom ones are all primed, and primed. And this is mu nu k. And this is, of course, rho sigma eta, rho sigma and eta, which are these 3 downstairs indices, and then times the Riemann tensor again, but without any prime, so times R lambda mu nu k. Right? Lambda, and then mu, nu, and k. Right? So this is a genuine tensor. Right? It is, of course, a 4-index tensor. Right? So in this particular form, it is contravariant in the first index and covariant in the remaining indices. Of course, remember that you can lower and raise these indices just by using the metric. So you can just multiply this by the metric and bring this index down to here, right? And that would be an equivalent form, and the transformation law would be slightly different, but almost identical. So this was, of course, a big discovery, and that is something that Einstein initially was unaware, right? Through the Einstein-Grossman collaboration, they learned about all these wonderful things. And they were able eventually, right, because of that, they were able to bypass this impasse that g mu nu semicolon lambda was equal to 0. Right, so g mu nu semicolon lambda is equal to 0 was bypassed, right? Because you do, in fact, have an object that is made out of the, what we would say now, the gravitational fields, right? The gravitational fields enter in the gamma, right? You do remember that the gamma is 1/2 times g to the minus 1 times some suitable combination of derivatives of the metric, right? And so that appears everywhere. So that means that this thing, you know, contains the metric in actually a very complicated way, right? Because you really don't want to write out this thing explicitly because it's really quite a bit of work to do that, right? Each one of these terms contains that expression when written out of the metric. And here you have even terms that involve gamma squared, right? So that goes everywhere, right, in here. And it is, as a result, very complicated, right? So, so that's what it is. And so it is useful to construct simpler objects. So there are useful contractions of this r lambda mu nu sigma, right, of this Riemann tensor. And the first one that one can do is contract indices in the following way to define r mu k as r lambda mu lambda and k. So in other words, you take this index and you contract it with that one. So you set the two indices equal and then you sum over. And that is a two-index object, and this is called the Ricci tensor. And that is, in fact, one of the things that will appear in the field equations. The field equations, it turns out, do not contain the Riemann tensor explicitly with all the four indices, but only the contractions that involve two of these indices. And you have to do the contraction in this way because if you contract the first and the second index, you get 0. Because there are certain symmetry properties to which we'll come in a moment. That is, the Riemann tensor is antisymmetric in certain pairs and symmetric in some other pairs. And if you contract the wrong way, then you get 0. And so that's the first thing you can do is contract the first and third index. And the other thing you can do is now contract this guy, the Ricci tensor, one more time. And so do g mu nu times r mu nu. And this is called the Ricci scalar. Or sometimes just a scalar curvature. Ricci scalar or scalar curvature. Right? So you can, in fact, make a scalar out of that tensor, which, as we'll see later on, describes some sort of average curvature, because by doing this trace, you're just summing all different components of the Riemann tensor, so you do some sort of averaging, right? So we're not done yet entirely with some of the mathematics. We're going to come back to the symmetry properties of the Riemann tensor in a little bit, but before we do that, let me talk briefly about parallel transports, and in particular parallel transports around a closed loop. So parallel transport around a small closed loop. That is, what we talked about in the previous lecture was what happens when you take a vector, for example, S lambda, and you parallel transport from point A to point B, right, along some path which is given by some x mu of tau, and you find that this vector is the way it rotates is determined by the equation for parallel transport and therefore by the affine connection, right? And so now we're going to look at a slightly related scenario where we actually do the parallel transport around a closed loop. So we start out with a vector and we parallel transport it like this. right? So we have an initial vector here, and it's going to point in some direction. And as you go around this loop, you will find that the vector does not come back to itself. So it generally will come back to some other orientation, which you can write as some sort of dashed line, right? And so I gave an example of this in the last lecture, right? I mean, I do understand that, you know, it was hot and the winds were blowing hard and all of that. And so, you know, the example I gave was the case where you do start out with a vector, right? And start out here, right? So you have a vector that is pointing this way. And now you do the parallel transport. So it means as you're walking, you're just keeping this vector always pointing the same way. And so you traverse this loop, and the vector gets parallel transported to itself. And of course, if you are in a flat space, you end up exactly where you were, right? So you go around like this, and the rotation angle is 0, right? But if the manifold has some curvature, right? So if it looks like, say, a section of the Earth, right, somewhere around here, North Pole, or wherever it is, right, then the manifold will look a little bit like this, right? Now, it's hard to do a curved manifold with a piece of flat paper, right? But we can still model that by just having some sort of conical singularity at the origin, right? And so if the manifold looks like this in the vicinity of this point, then as we do this parallel transport, we start out this way, and as we go around, we find that there is a mismatch because the original direction does not coincide with the final direction. So this parallel transport of a vector around a closed loop is in fact a way by which you can detect curvature. You can detect curvature locally by this exercise. And so we might think that this would be something that can be expressed in mathematical terms. That is, that we can take a vector, parallel and transport it around an infinitesimal loop, and that somehow that will detect the curvature at that point. And the thing is that the curvature is, of course, related to the Riemann tensor, so we should get some components of the Riemann tensor out of this, right? And so we're not going to go to derivation. You can find the derivation of this in the book, and it's actually fairly straightforward to do that. But it will use, the derivation uses the analog of Stokes' theorem, right? And Stokes, so it's the gravitational analog of that. Now, you remember that the Stokes' theorem says that if you take a vector, right, and you transport that vector around a closed loop, which looks like that. Right here is the vector, we call it A, right? And so this is some sort of circuit, which is denoted by C. So that's going to be our circuit here. That this can be expressed as a surface integral, right? So you can write it as an integral over, so this is our circuit right here. And then there is some area inside of that. So we can write it as an integral of A, and with the curl of A dotted into n times the surface area element, right, dA. Right, well, there's too many A's here, maybe, so let's write this as d sigma, and so this is the area, so let's give it some other name as area like this. Right? Now, the essence of Stokes' theorem is that you can convert a line integral into a surface integral. So we're going to convert it into a surface integral. And the price you pay is that you're going to get a derivative of the field, or more specifically, in this case, of a curl. So here we're going to have something similar because we are going to integrate along a closed circuit. And what appears originally in the parallel transport equation is the affine connection, and we're going to get the curl of the affine connection. The curl of the affine connection is essentially the Riemann tensor. Right? So the result is that if you do this parallel transport around a closed loop, then if we have a vector that we call S, right, then the change, we can talk about the change in the vector S, which is what I just indicated through that demonstration. Right, so this vector is going to be changed by some amount, which is delta S lambda. right? So that S prime lambda is equal to S lambda plus delta S lambda, right? So this delta S mu is equal to 1/2 times the Riemann tensor R sigma mu nu rho. Indices in this combination, again, it is useful to have the first index upstairs, times S sigma, and then times U rho nu. So this part is the Riemann tensor, right, at that point. Well, where? Well, around the origin here. It's an infinitesimal loop. It's an infinitesimal loop. So the x here refers to the center of the loop. And, well, the change in the S is going to be proportional to Riemann tensor, is going to be proportional to the vector itself, of course. So this can be written as some sort of rotation matrix eventually. And then times this object here, which is the analog of n times the normal to the surface times the surface area element. And so this is called the area bivector. The area bivector. And so that is because we are in 4 dimensions, right? In 3 dimensions, the area, if you're looking at an area element, there is a normal which is perpendicular to it. If you do it, of course, in 4 dimensions, there's 2 normals to it. There's 2 directions. That if you have a surface, it's a 2-dimensional manifold. And so perpendicular to that, there's not 1 direction, but there's 2. That's why you have 2 indices. So this area bivector, U mu nu, is defined as the integral around this closed path of U mu, sorry, x mu dx nu, like this. So you have to do this integral of the coordinate around this closed path. And so in particular, if you have just a square, right, the simplest thing to work out for that integral is just a parallelogram. If you have a parallelogram with sides A and B, right? So if we take something that looks like this, so this is x, and this is x plus dA, and this is x plus dB, and this is x plus dA plus dB. So these are 4 vectors, right? So we have dA mu, and we have dB mu. Right, these are 4 vectors. So if you look at a parallelogram like that, then you're doing the line integral along this path, right? And so you can evaluate that, and the result is that U mu nu. Again, it's an exercise by which you evaluate each of those legs individually, right? And then you add them up to get the integral, and then this is equal to dA mu dB nu minus dB mu dA nu. So it's just a product of these components, right? And so that is what goes in here, right? There's nothing to do with the for velocity, right? The for velocity is something else. So this is just this area bivector, which is related to the lengths of the sides. In fact, you can work out the square, and the square is minus twice the area. So you can do this exercise of calculating U mu nu, right? So you take this object and you dot it into itself, and you do the dot product the correct way, which means having indices upstairs in the first term and downstairs in the second term, or vice versa, which would work out the same way. And this is minus 2 times the area squared of this thing. So this has a certain area, right? And so the dot product of that is the magnitude of the area. So you can also, if you want, introduce a normal to the surface of the unit u mu nu by dividing this by the area. Each one of the u divided by the area gives you a unit vector. So anyhow, let's go back to this result, because I think this is one of the fundamental results, again, in differential geometry. And that is that if you do, for any manifold, right, it doesn't matter what it looks like, if you take a vector and you parallel transport it around a small loop, around the point x, then the amount by which the original vector does not come back to itself, right, this delta s, that will give you the components of the Riemann tensor at that point. Right? And now you can see, in fact, why the Riemann tensor has so many indices. Right? It has so many indices because in order to determine completely what the curvature would look like at a given point, you got to do this transport in all sorts of different directions, right? Because we are in four-dimensional space-time, right? So it's actually 4 dimensions. So how many planes can you have where you do this parallel transport? Well, there's lots of them, right? So as a result of that, there's all sorts of different components, right? So you can see here that the 4 components of the Riemann tensor have to kind of be there, right? Because first of all, the surface area element in 4 dimensions has to have 1 index more, because there is no such thing as just a simple normal to a surface, because we are in 4D, so there's 2 directions. So there's 2 indices here. Of course, the vector itself has 1 index, right? And so this object has to have, naturally, has to have 4 indices, right? It cannot be any simpler than that, right? So the geometry of 4-dimensional space-time kind of forces you to have, if you want to describe the curvature locally, forces you into having an object that has all sorts of different components, and we have to live with it. So that means that, again, you know, we encounter this situation that gravity is more complicated than electromagnetism, right? In electromagnetism, we got away with having just a field with 4 components, right? A mu, vector potential, and a Coulomb potential, right? And here we have G mu nu, which has 10 components. The electromagnetic field is just E and B field, that's 6 fields, right? And here there's quite a few more, because in fact, if you start counting how many components there are to that Riemann, there's 20. There's 20 of them, okay? So there's actually quite a bit of components that one has to obtain in order to determine uniquely what the curvature is at each point in space. Right. So now there is a theorem. There is a theorem. And the theorem says, and I'm just going to say it in words, that the necessary and sufficient conditions for a metric at a given point in space-time to be equivalent to a Minkowski metric, so necessary sufficient condition for G mu nu to become an 8 alpha beta, right? So what are the necessary and sufficient conditions for space-time to be flat at a given point? Well, there's 2 of them. The first one is that the Riemann tensor has to vanish. R lambda mu nu sigma is equal to 0. And that, of course, is a function of the metric, right? So it implies some sort of constraint on the metric. And there is a second constraint, which is also fairly obvious, and that is that the G mu nu has to have the right eigenvalue structure. That is, it has to have 3 positive eigenvalues and 1 negative one. Right, so the metric is not going to reduce to the Minkowski metrics if you get something that looks like -1, -1, and +1 along the diagonal, right? But perhaps the most important one, we're usually not going to get into this kind of pathologies where it doesn't reduced to the flat metric, right? The most important condition is the first one. And so if the Riemann tensor vanishes at a given point, then it means that around that point, space-time is flat. That was not the case when we looked at the affine connection, because remember the affine connection, even if you had a manifold that was curved, some components of the affine connection were non-zero, and that has to do with the fact that the affine connection was not a tensor. Right? It was not a tensor. So you choose some weird coordinate system, like analog of spherical or cylindrical, you all of a sudden find that certain components of the affine connection are non-vanishing, even though the space-time is flat. But Riemann will tell you exactly whether it's locally flat or not. So if Riemann is 0, then space-time is flat at that point. So we have just a few minutes left, and so in those remaining few minutes, let me list the so-called algebraic properties of R mu nu. So from the definition of the Riemann tensor, so from the definition of R lambda mu nu sigma, right? And you do remember that the Riemann tensor was something like the derivative of gamma minus the derivative of gamma plus gamma gamma plus gamma gamma, right? It looked like this, so it was quite a mess, but nevertheless, its expression was given explicitly previously. And so you can actually, and do remember also, right, that gamma was equal to 1/2 g to the minus 1 of dg plus dg minus dg, some combination of that. So you need to stick this in everywhere and then stare at the object for a while. And one recognizes, this was something that was recognized early on by Riemann and Christoffel, is that there are a number of fundamental properties of the Riemann tensor which has to do with the symmetry under index exchange. And so it's antisymmetric in the first and second pair. Right? These properties will turn out to be quite useful. And so if you take R lambda mu nu k, then this is equal to minus R, you interchange the first pair, so minus R mu lambda nu k, and then you interchange the second pair and you get back to what you had, which is R mu lambda k nu. And this is equal also to the original, so you swap these indices, right? And so it is also equal to minus R lambda mu k nu, right? Where you swap the second pair of indices. So if you swap the first pair, you swap the second pair, you pick a minus sign. If you swap both of them at the same time, then it stays the same. So it also has a swap symmetry between the first and the second pair. So in other words, if you take R lambda mu nu k again, and so what you do is you swap this pair with that pair, and so then it stays the same. So this is R nu k times lambda mu. So if you swap the first with the second pair, then it's unchanged. If you swap the first two indices or you swap the second two indices, then it changes by a sign. And the property C, it has the following cyclic properties. Cyclic property. And I'm going to write that over on this side, otherwise you can't read it. And so that is a little bit like a property that we wrote before for the F mu nu of electromagnetism. And so it has to do that when you write R lambda mu nu k, now with all the indices downstairs, you can cyclically permute these last three indices, and when you add up the three contributions, you get 0. So plus R lambda, so let's put the k here, and so you get k mu nu. and then again swap this one, so you get R lambda, and then nu k mu, and this is 0. Okay. So there's these algebraic identities, which means there are 20 algebraically independent components of R lambda mu nu sigma in D equal 4. So well, let me just mention one last thing, because then next time we can move on and do something else. And that last thing that I want to mention is the Bianchi identity. So there is one differential identity there is one identity which you obtain by taking derivatives. These are just algebraic properties, but the next one has to do with the derivatives, and there is both a contracted and an uncontracted form. So let me just give the one that will be useful later on, and that is a contracted form. We're out of time today, so and you can read more about this in various books. And so it says that if you take Riemann, well, not Riemann, but one of the contractions of Riemann, which is this Ricci thing, right? So let's take R mu nu, right, which is where you contract on the first and the first and third index of Riemann, right? And then if you subtract from that the G mu nu times the Ricci scalar, right? Then what Bianchi found is that the covariant derivative of this is identically 0. And so this is called the Bianchi identity. And this will play an important role in the field equations, in fact, in the next lecture. And so there is a differential identity, right? So when you take certain derivatives of the Riemann tensor, they're related to each other. They're related. And in particular, if you use this Ricci tensor, then a covariant divergence of the Ricci tensor can be related to a covariant derivative of just the Ricci scalar itself. And that was one of those identities that was derived just before Einstein came along, right? This identity became known, I think, around 1901 or 1902, and was published probably in some obscure differential geometry journal in Italy or wherever it is, you know, the proceedings of the Venetian Academy of Sciences. And Einstein did not know about this until the very last moment, until when he had written down the field equations, he at least the first form of those, he wasn't quite aware of this Bianchi identity. And then people pointed out to him, look, there is this one more thing that you're going to look up in one of those dusty math journals that might be relevant to our problem, and that has to do with certain divergences of Ricci being related to this. And so that's an important identity. All right, I think that's enough for today.